Okay, so hello everybody. My name is Óscar Lapuente-Santana. I'm a PhD student at TU Eindhoven in the Netherlands, and I'm very happy to be here presenting the work of my team, the cSysImmunoOnco team. I just realized it's a very complicated name. And I will be talking about systems-based descriptors of the tumor microenvironment for prediction of disease progression in anti-PD-1 treatment. So tumor cells produce antigens that are recognized by the T cells to generate anti-cancer immune response. However, tumors develop mechanisms of resistance, such as upregulation of immune checkpoints, to cancel out this immune response. This happens as a consequence of the generated immune response by the T cells or by intrinsic mechanisms within tumor cells, such as mutations. Immune checkpoint blockers leverage this knowledge, targeting these checkpoints with antibodies, aiming to restore the anti-cancer immune response. However, this type of immunotherapy has achieved long-lasting responses, but only in a subset of the patients. Given this, it is of paramount importance to look for biomarkers and to understand the mechanisms of resistance to assign the immunotherapy to the right patients. Also, understanding the mechanisms of resistance will lead us to design new combinatorial treatments with improved therapeutic efficacy. We should understand tumors as complex ecosystems made of different interactive parts. For instance, the tumor microenvironment consists of multiple cell types that talk to each other. Such a perturbation, such as cancer therapy, will propagate through the system, and we cannot understand this using individual genetic markers. So system biology approaches can characterize the emerging behavior of these interacting parts. Traditionally, gene expression has been used to develop models for prediction of treatment response. Here, we combine gene expression with different types of prior knowledge that is available in literature or in databases to build system-based signatures of the tumor microenvironment that we use to build our models for treatment, for prediction of treatment response. In particular, we have derived 5 quantitative descriptors, such as immune cell quantification, which is based on the convolution of RNA-seq using immune cell signatures. Pathway activity and transcription factor activity was inferred using knowledge on network structure. And we also derived cell-cell communication features using curated literature about ligand receptor interactions. We wanted to leverage the widely available bulk RNA-seq data there. So we therefore refer to the TCGA. However, only a subset of the patients in the TCGA have available response to immunotherapy. So then we decided to look into literature for published scores, and we found actually a lot of them. What we realized is that these different scores were looking at different points of the immune response. So we decided to take them all. And therefore, we build models that aim to learn the relationship between these signatures of the tumor microenvironment and these proxies of immune response. And we did this in a cancer type specific fashion. We learn our models using a regularized multitask regression algorithm, in which our input data will be our features of the tumor microenvironment, and our output data, given that it's a multitask problem, will be, instead of a vector, will become a matrix with containing all the proxies of immune response. We tune our hyperparameters using a 5-fold cross-validation. We assess the stability of the models using Bootstrap. But then maybe the novelty here was we want to learn all the tasks, the proxies at the same time, and thus we use a group elastic net penalty for that. So we selected features that are relevant for all the tasks. We put all this together into a framework that we call Estimate Systems Immune Response EaSleR, which is available as an R-bioconductor package, and users just need a bulk RNA-seq data from patients, and EaSleR will return the systems biomarkers of immune response for each patient, as well as the likelihood of immune response for each patient. We have validated EaSleR in 4 different cancer types. Here I'm just showing the results for a melanoma cohort of 50 patients. Here on the left, you can see the predictive performance of each individual descriptors. Also the ensemble model combining these individual descriptors. And also our descriptors were able to outperform the proxies of immune response. Additionally, these signatures of the tumor microenvironment allow us to identify mechanistic biomarkers. So for instance, here, if you look at the cell fractions, as expected, we find CD8 T cells as a higher biomarker in responders patients. With respect to the pathways and the transcription factors, we found JAK-STAT signaling and transcription factors related to this pathway in responders patients as well. So we need bulk RNA-seq data as input for EaSleR, and EaSleR will return an estimation of immune response. Tumor mutational burden is an FDA-approved biomarker, and it basically represents a measure of tumor foreignness. These two biological processes are complementary to each other. So both are required for successful immunotherapy. So we need both to have the neoantigens there and also to have an existing immune response in the patients. So we combine these two scores to derive an anti-PD-1 response score. Here I'm showing the results for 3 different cancer types in 4 cohorts. And basically, I think you can see the gold line, the predictive performance, in gold, the EaSleR performance, in red, the tumor mutational burden performance. And the dotted lines basically represents the combination. And we can see at the middle where the relative weight is 0.5, where both, which represents that actually we need both to achieve the highest performance. So both contribute equally to our score. This was the approach that we used in the challenge. Since we were building cancer-specific models, we stick to the non-small cell lung cancer model to achieve a likelihood score of immune response. We use the tumor mutational burden to get our score of tumor foreignness. However, there were some patients where the tumor mutational burden wasn't available. So we use instead a transcriptomic signature of microsatellite instability that we already checked in the TCGA that was having good correlation in lung cancer patients. And we combine this, as I mentioned previously, to achieve an anti-PD-1 response score. And using this approach, we rank as top performers in sub-challenge 3 in prediction of disease progression. Yeah, and with that, I would like to thank the organizers of Anti-PD-1 Response Prediction Dream Challenge. It was really an awesome experience. And especially I would like to thank my team, my supervisor, Federica Duarte, also from TU Eindhoven, and our collaborator, Francesca Finotello from Medical University of Innsbruck. And with that, I'll be happy to take any questions you have.